Hi, welcome to the fill in the blank notes for lecture number 2. So without any further ado, let's get through it. So the lecture started off with a talk about intellectual property. You can read all that. We talked about problem solving and that there's a typology of problems. I go from simple logic problems, story problems, which are interesting but not overly complex. And we're interested in this domain of problem-based learning down here, where we're looking at ill-structured problems, dynamic meaning they change over time, and fairly complex. And we gave some examples in class of logic problems, decision-making problems. This is the drink water problem, policy and strategic problems, Tim Hortons and the Burger King deal. We looked at dilemmas, so on and so forth. So that was a little discussion of problems. And adding to that discussion, of course, is wicked problems. And the definition of wicked problems is itself a wicked problem. These are problems like education, environment, poverty. They're all intertwined with one another. And I give an example down here. Poverty is tied to education, education is tied to nutrition, nutrition is tied to environment, environment is tied to economic activity, and so on and so forth. It's a wicked problem. If you try to unpack one aspect of the problem, you end up with all kinds of other things in this kind of situation. So one of the things that can help us deal with wicked problems is systems thinking. And before we get into systems thinking, let's contrast this with process thinking. So process thinking is fairly straightforward. You have inputs, you have some sort of transformation process on those inputs. Some of the inputs may in fact be consumed in this transformation, and then finally that leads to some outputs. And I gave a little example of going out to Alberta on a trip for my brother's wedding and some of the things that happen along the way. So we talked about that story, and here are some examples of process thinking. So when we look at physical transformation, one of the examples I gave was a raw steak. So we went to the restaurant, they gave us a raw steak, and you put it on the grill. So there's some sort of fuel, natural gas in this case. There's a physical transformation of the steak, and then you end up with a cooked steak, which is physically different from its original steak. The fuel is no longer there. It's been consumed in the process. We gave the example of locational transformation. This one happens all the time. So again, you might have an airplane, a pilot, jet fuel, passenger, and any number of inputs you want to consider. Again, a locational transformation, you're moving from one place to another and actually creating something new on the other side. So the fuel again has been consumed. The end product, the output, if you will, you could say, is a happy traveler. They've made it to the destination in time. The plane is still an output of that, the pilot, and so forth. What we're not looking at is everything that comes before this and everything that happens after this. I'll talk about that more in a moment. Storage transformation. Again, a lot of times you hear about storage transformation and you go, it's bad. Right? This deals with the time element. So if you think about inventory sitting on a shelf, we have to get that inventory moving, got to turn it over, we can't have those vegetables sitting on the grocery shelves for too long. But here's an example of a storage transformation. If you take water, yeast, barley or malt, and hops, and mix them together and then have a storage transformation, you end up with a new product, namely beer. Right? You can't have 12-year-old scotch without 12 years is sort of the example I always use. So storage transformations, just by putting something together and leaving it over time, you'll have a transformation. I gave an informational transformation. The example I gave was my brother's fiance, my brother, and an officiant. And at the end of it, we still had a female and a male, but now they were married. So we've just changed the information, we've changed the data. So that's one example dealing with people. These things happen all the time dealing with numbers. So you take a stack of numbers, add them up at the end. This process creates new information. It's an informational process. And finally, give the physiological transformation. I was hungry, and then I ate the raw steak from up here. Oh, no, I didn't eat the raw steak. What am I saying? I ate the cooked steak. That's better. And then I was full. So physiological transformations happen all the time too. You have sick patients, and they undergo medical treatment, and then end up physiologically transformed into healthy patients. So that's an example of process thinking. When we start looking at things that come before, things that come after, and how this relates back to this, when we get this cyclical kind of setup, we're now looking at systems thinking instead of process thinking. So let's move on through the notes. Give a quick example of that. Talked about it in class. Systems. Systems have a few defining characteristics. They have some element or parts, elements or parts. And these are fairly easy to identify. All of these elements or parts are interconnected. So one part affects other parts, and so on and so forth. And these two parameters in and of themselves are interesting, but what really defines a system is it has some function or purpose. And we gave a few examples of these. One example is you've got, a hand of a watch and a gear and springs and all that kind of stuff. They're interconnected in some particular way into the watch, and it has the purpose of telling time. Gave an example of Elaine Campbell, who is a double lung transplant recipient. There's a number of elements in the system: the lungs, the heart, nerves, body, all that kind of stuff. They're interconnected, and they perform a particular function, namely keeping her alive. And you can interchange some of these elements. If you take out a person's lungs and reconnect them the same way, so this interconnectedness remains the same, you can still have the same function at the end. So that's one of the key ideas of systems. There's a few more. Another example we gave was of a ping pong game. And ping pong, we have a few identifiable elements. So we have, player 1 and player 2. So you need 2 players for ping pong. Otherwise, it's not a ping pong game. It's a practice or something like that. It's not a doubles game. It's easy to identify the gear, paddle and a ping pong ball, and the ping pong table. So those are the basic elements. There's interaction. So the player holds on to the paddle to hit the ball. So there's laws of physics involved, perception, things like that. Likewise, player number 2 has their paddle hitting the ball interacts with the table. There's elements of strategy and psychology happening between the different players. Just a few other bits. We have the elements, which we can identify, the interconnections between them, and then the purpose. What's the purpose of ping pong? Well, you could say it's a fun or game or sport or recreation or competition, all those kinds of things. So you can identify some function. So ping pong would be a system. And again, we have identifiable parts like paddles and so on. The parts affect one another. So the ball hitting the paddle impacts both the ball and the paddle, and so on and so forth, through the laws of physics. Together they create a unique experience. If you take all of these bits, you have a unique experience called a ping pong game, and the effect can be replicated multiple times. So you can have another table and another 2 players, another set of paddles and balls, and have another ping pong game. So you can multiply this number of times. If you change something out or add something in, so for example, you put in red Solo cups and some beer, you now have, right, beer pong. So it's a completely different game by changing up some of the elements. So those are the basic ideas with systems thinking. So I'm going to stop this video here.